Sieves are easy to see for coarse particles. You have, right? You basically have wires running around. Depending upon how many wires and how wide the wire is and how closely they are spaced, you'll have space between the wires. And if you have like, you weigh out an initial amount of particles and you slowly increase the number of wires, you reduce the spacing, you look at how much material is left behind in the coarse, the fine, 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 and you can get a distribution of particles in that manner, right? And there's a way to be able to control or standardize the number of wires, the opening between these wires, and what size exists. And usually you can say if it's a minus 100 mesh, right? This means that you're below 150 microns in this case, okay? Just and so you can get a distribution, right? In the case of sieves, but you can get that type of a distribution with any of the other techniques, whether it's light scattering, right? Whether it's sedimentation, whether it's X-ray diffraction, and so on, right? And so mainly you provide a a cumulative frequency distribution, and so then that's defined by a median, and then also different how much coarse is there, how much fines are there, right? So in terms of streaming, right, you have particles in a fluid, they flow past a detector, they block off some of the light. Larger particles will block off more light than smaller particles. And so using that principle by measuring the detected intensity and how it changes with time, you can get a measure of particle size distribution just from blocking. And then there are different parameters depending upon the so you have a laser beam, it goes through the stream of particles. You have multiple detectors in different regions, and so you can get a feel, because if it is platelets and they're all oriented along the edge, it's going to leave most of the light through, but you need this opposite direction, right, of the plate. That's going to block off a lot more lights. So you need for irregular shaped particles, you will need from different sides to and correlate that information of light intensity change with particle size distribution. And of course, if you change the wavelength of the light, you can be able to measure scattering for different particle sizes. So going back to the different types of ion powders that we saw, starting from water atomized, gas atomized, carbonyl ion, centrifugal atomized, you can see that different synthesis methods are giving quantitatively very different distributions. All these, or most of these, are spheres, right? And this one is irregular shaped. But you're going to get very different distributions. It's not just the median, and now being able to know that is going to affect the packing behavior and then the sintering response, right? So in terms of cumulative distribution, for instance, you need to know the median. Then D10, this is the terminology. D50 means 50% of the diameter is below this particular value. Of the particles have a diameter below this value, right? So 50% of the particles have a diameter below about 8 microns, right? D10 means 10% of the particles have a diameter, right, below this, right, about 3 microns. Right? D90 means 90% of the particles have a diameter below about 11 microns. Right? So that's how you take, and then of course D5, D20, D80, right? That's what this term D10, D50, D90, these things mean. And from that you can get a mean, you can get pretty much statistical properties of any distribution, right? And that is how you begin to define attributes of a particle chemistry. for continuous distributions. Right? So this involves refreshing some statistical information, right? How to calculate them, and when you do certain measurements, and how to relate that to defining the size of a particle. Right? So you can have broad distributions, you can have narrow distributions, and that's all going to change how the material behaves from there on. So you change chemical parameters, and this width of the distribution, whether it's a Stobel process or whether it's your chemical precipitation method, this width of the distribution has to be known as a function from a chemical engineering perspective, as a function of different synthesis conditions, and then relating that change to what is changing the catalytic properties or fuel cell properties becomes important, right? So you have shape diversity in powders. That's the central message. And it can be all, so these are all real powders, different SEMs, cubes through spheres, through rods, and so on, right? And this is more of a general map in terms of what are some of the common shapes that people can find depending upon different synthesis conditions, synthesis types. And so a scanning electron microscope is useful for up to like submicron ranges, but then you to go below to nanoscale, you have to go to a transmission electron microscope or a focused ion beam. Right? Surface area, relating it to the diameter of the particle, right? Right? The density and then the surface area become important, right? Grams per cc. And so accordingly, using surface area to define particle shape and particle packing become important, right? And so important to study sintering behavior, important to study catalysis, right? And so you can use BET, but there are other methods as well available. In BET, you're looking at gas adsorption, and depending upon the surface area available, you can absorb more gas particles. And there are isotherms that are available as you change pressure and temperature, and you can get coverage of gas molecules, right, by desorbing them. So density, packing density, right? So for that you need apparent density. Apparent density means you pour some material into a given known volume, how much space does it occupy? Okay. So also called as bulk density. So it's loose packing behavior. Tap density is you begin to shake it and you add a little bit more powder and then you keep shaking until you reach a particular limit. So depending on how long you shake it and how much you and how and there are standardized tests for that, right? You can end up measuring packing behavior from tap density. You can take powder and you can apply pressure to that, and up to a certain point you can increase the density. Depending upon the initial density, the final density is going to change according to pressure. And so that could be another way to define packing behavior. There's a limit to which you can, which depends upon the initial packing, it depends upon the mechanical properties of how deformable the powder is. That's going to limit how much material you can pack, right? I'm traveling, I have some clothes, and they're not fitting into the bag. So I sit on top of the bag, and then maybe like you can close the thing, right? So you apply pressure. Right? Pycnometer density, helium pycnometry is a technique by which you can measure the theoretical density of individual particles, right? Which depends upon the chemistry and things like that. So mass, then it goes back to the original mass per unit volume. Right? But in each case, it's also, they're all densities, but what is the mass? What is the volume? Right? So this is a range in which all of that can change. Right? So different techniques. So this Arnold meter will allow you in a known volume, a weight of material will be weighed and filled into that exact volume. And so mass over volume will give you apparent density. Okay, so this is a standard test. There's a particular block with a hole in it, and you fill it exactly with a certain amount of material. You take that block away, and the weighing paper below, you go and weigh how much is the weight of the powder, you know the volume of that entrance, and so you have packing information. Tap density, there are standardized tests where you take a measuring cylinder and you clamp it down with the powder, okay, and then there's a vibration intensity and vibration time, how fast you tap it and how long you tap it for. No, in this case it's just mechanical vibration. It's just this cylinder fills with powder and it's clamped down and it just moves up and down, right? And so with the mechanical vibration, um, you find out after that whole test how much is a new volume. You have put a known weight and mass over volume, you can get tap density. This is compaction density, right? So this is how the density of the powder varies as a function of powder compaction pressure. And there are two different kinds of powder chemistry synthesis. This is water atomized powder, this is reduced iron oxide. And you can see that depending upon the initial powder characteristics, depending upon the synthesis condition, the response of how density changes as a function of pressure is going to be quite different. So compaction response. So you can look at compaction density as a way to characterize powder packing behavior. But also you know now if I change the powder shape based on powder synthesis conditions or the powder size, the final density of the part that I'm going to make is going to change a little bit. The porosity of the part is going to change. Right? Sometimes you want high porosity, sometimes you want low porosity. Here's an example again of now you made the parts at different densities. You want to now look at the strength of that part. Right? So strength as a function of compaction pressure. And so you had very small differences in density, but you can have very high differences in the strength between the, of course the scales are different, but you can see that you make two powders differently, they have different attributes, how strong they are and how much pressure is required to get them to a certain density is going to change, processing going to change. Right? Again, here in this case is alumina and how it is dispersed, and depending upon again the particle sizes and the dispersion, you can have large pores or you can have uniform dispersion. Crystallinity is a final attribute that I would like to touch on. And so, you know, from just looking at crystals and how pretty they are and all that, right? Different minerals, a lot of minerals in Brazil, right? You can have very different kinds of shapes, colors, sizes, right? And then, of course, if you go to carbon itself, so that's this diamond, and then you have graphene, graphite platelets, you have buckyballs, you have carbon nanotubes, right? Different morphology, very different properties, right? Very different costs. And then finally nanoparticles, right? With us make palladium, we make tubes, make wires. You can make a whole lot of by adjusting the chemistry now, you can have a huge number of, these are all same chemistry, very different particles. Or you can have a long, very unlimited range of chemistries and hence properties. What do we do with that? That becomes a challenge. How we can make them, but how can you control them? And how do you know what to make for a given process or given application? Right? That is the research opportunity to be able to understand many of these things. And so that's going to be the message with which I shall leave this lecture.